In the previous few videos, we were mainly doing this kind of interpretation of faults and horizons, and the operations or the procedures that we have gone through mainly uses the original amplitude, right? So this most of all the interpretation we have done so far are based upon just this one volume, right, which is the original amplitude. Right? Um, but sometimes the original amplitude is probably not the best volume for 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 picking, for example, horizons or faults or some other structural features, right? So, and another thing is that the seismic volume, the original the seismic survey, seismic surveys are actually usually quite expensive. So, what you want to do is to actually make the most out of a seismic data set, right? For example, this particular three-dimensional seismic data set, you wanna make the most use of it, right? And so Petrel actually provides several capabilities for you to actually derive seismic attributes from the original amplitude, right? And the seismic attributes can be quite helpful, right? They can be quite helpful for us to actually do interpretation, do structural interpretation, right? Pick horizons and pick faults, right? Some of the structural features which might not be very obvious on the original amplitude of cube can become quite obvious if you actually do some kind of if you actually extract the attribute, right, and then try to pick those structural features from the attribute of volume, right? Um, and those attribute volumes allow us to actually not just discover useful structural features, but also can be quite useful for us to, for example, when we try to do petrophysical modeling, right? Those seismic data could provide quite good constraints in regions, especially in regions where the well data or the well log data are not so good or dense, right? So seismic data and its attributes provide us those kind of a global those kind of an overall constraint about a particular region. But what exactly are those seismic attributes? Right? Those seismic attributes, you can think of it as just some kind of a subset or some kind of a property that's computed from the original amplitude through some mathematical transform. But those mathematical transforms usually have good correlation with geological meaning or geological understanding of a particular region. And the calculation of those attributes are actually quite easy, and Petrel can actually do those calculations automatically for us. We don't have to all we have to do is to specify the correct input. Right. So in Petrel, we have two kinds of attributes. One is called volume attributes, which is actually inside of this particular button. If we click on it, it's going to give us a dialog box for us to actually pick and create volume attributes. A volume attribute is going to, if we use the volume attributes to compute a certain volume, then the result is going to look like a cube, just like this kind of volume, right? Seismic volume. But the color is going to display the particular computed attributes instead of the original kind of amplitude, right? But sometimes we would like to extract attributes that's kind of associated with a particular surface, right? So suppose we have some kind of a surface interpretation, right? We would like to actually, for example, compute a certain attribute that is sort of for a certain time interval or time window that goes from like 10 milliseconds above the interface to above the horizon to like 20 milliseconds below the horizon, that kind of thing. Those kind of attributes are kind of attached to a particular horizon or particular surface, right? And those kind of attributes are called a surface attribute. right? And then Petrel actually provides a button for us to actually compute those surface attributes, right? So we can either compute volume attributes or surface attributes by using these two buttons, right? And each of them has its own utility, and it can sometimes they serve different purposes, right? That's like two kinds of attributes that we can extract, right, from seismic data. But if we actually look into each of the button, for example, if we look into the volume attributes, let's take a look at what's actually inside of this attribute dialog box, right? So the first thing you might have noticed is that we have those buttons. We have seen those buttons, right? This allows you to add a row. This allows you to delete a row, that kind of thing, right? So this part of the box allows us to actually insert multiple volume attributes, right? And we can actually, for each of them, we can actually define different kinds of attribute that we want to extract, right? For example, for the first one, we might want to compute the, say, instantaneous phase. The second one, we can compute the RMS amplitude, and then for the third one, we might want to compute, say, sweetness, that kind of thing, right? So this part of the dialog box allows us to actually extract different kinds of attributes, right? And each of those attributes are going to be a three-dimensional cube. And for each of the for different attributes, there might be different inputs and outputs, and then parameters that we might want to adjust, right? Those parameters, those input outputs, are specific to the particular attribute that we are trying to compute, right? For example, if we select the sweetness, right, sweetness, and then in the parameters tab we have this thing that's called a window, and then we have a slider bar that can allows us to actually adjust the window width, right? And what's going to be the effect of adjusting this kind of window width? We're going to look at those kind of things later on, right? And then if you don't really know what's actually the meaning of those attributes, the question mark gives you some very short explanation about how those attributes are computed, right? For example, RMS amplitude, it's going to compute the IMS, the root mean square, on instantaneous trace sample over a specified window, right? What's going to be the width of the window? So by default, it's going to be like some value, right? So by default, it's like 9 samples, that kind of thing, right? If you click on it, if you click on one of those rows, it's gonna the parameter is gonna adjust to that, to the default value of that particular. So if you do click here, IMS amplitude, that's 9. The window width is 9, right? And then if you click on sweetness, then the window width is like 13 or something, right? And then if we click on instantaneous phase, then the default width for the window is like 33, like 33 samples, that kind of thing, right? And then we have realize, this checkbox realize. By default, it's not clicked, which means that all those volumes, all those cubes that's going to be created for instantaneous phase, RMS, amplitude, sweetness, are not going to occupy any kind of disk space. It's just computed on the fly, right? So it's just it's rendered on the screen that you can see the effect, right? But it's not creating data that's going to be stored on the disk, right? The reason is that sometimes you need to actually make adjustments to those parameters in order to actually get the best visualization effect before you actually try to realize, right? So if you actually realize it by default, then every time you change the parameter, it's going to create a new volume. If you try different values, try like 10 different values, then it's going to be like 10 different volumes. It's going to waste a huge amount of a disk space. So that's not a good idea. So what people usually do is that we pick a certain attribute and then try different parameters and then try to find the best effect, and then we have a we have a we have a separate option by right click on that particular attribute volume. We can select realize after we have found the optimal parameter, right? And then we can realize it to a disk, and then next time we can just do volume rendering, volume or cross section rendering, that kind of thing, and then try to make interpretations use those attribute volumes. Right? So um, so we can compute multiple attributes in the same run, right? And this button allows us to actually delete, to remove those attributes, right? For example, if we want to get rid of it, get rid of some of it, you can just use this button to remove those attributes that we don't really want to compute. So now let's look at what's actually inside of these two boxes, right? We have two boxes. One is called category, and then the other one is called attribute, right? So if we look at underneath what's actually the category of the attributes, if we just select all, then the attribute list is going to be huge. We probably have like close to like tens of attributes that can be computed by using Petrel, right? Petrel provides all those kind of attributes, right? But how those attributes are kind of different from each other, right? What's actually the purpose for those different kinds of attributes, right? So in this all category, it's just gonna sort of group all the. It's just gonna give you a list of all the attributes in the alphabetic order. It doesn't really tell you much about what's actually the purpose of each of the attribute and how they are kind of different from each other, that kind of thing, right? But if you actually choose a different category, then you can sort of, if you click on this button, or click on this triangle, you're going to see different categories of the attributes. For example, if you click on signal processing, and then the attributes that's associated with signal processing is listed, right? So this is pretty much just a subset of the all the attributes. Right? If you select all, and then a subset of this all the attributes that's listed here actually belongs to signal processing, right? For example, first derivative, frequency filter, F graphical equalizer, median filter, original amplitude, phase shift, those things, RMS amplitude. So all those attributes actually belongs to the signal processing category, right? Signal processing just means that it just applies this kind of a time domain signal operation, right? Some kind of time domain operation. For example, first derivative, it's going to take a first derivative on the time axis. Frequency filter, it's going to apply a filter in the frequency domain, right, to each of the seismic trace. Median filter, original amplitude, that's without any kind of transformation now. The original amplitude, which essentially is a delta transform of the original signal, right? So it's not going to do any kind of operation on the seismic. So phase shift, RMS amplitude, reflection intensity. This might be a useful thing, right? Second, time gain, trace AGC, trace gradient, that kind of thing. So all those things are kind of associated with signal processing category. And then you have complex attributes. If you click on complex attributes, it's going to give you all the attributes that's kind of associated with complex transform, right? For example, sweetness, right? Sweetness is like something that's indicates the locations of the sweet spots, right? So sweet spots are kind of associated with locations, usually associated with locations of gas and oil, right? Hydrocarbons. So it's some kind of amplitude normalized by the frequency. If you sort of move your cursor to the question mark, so it's envelope. Envelope is just like some kind of amplitude information divided by square root of the instantaneous frequency, right? And this kind of attribute is based upon experience, right? People in the past, people have found that this kind of attribute are correlated with the existence of oil and gas. Right? Um, so complex attributes, right? And then you also have apparent polarity, cosine of phase, um, instantaneous phase. Those things are kind of similar, right? And then instantaneous frequency, so all those attributes are kind of associated with complex attributes, right? And then structural methods. Those those attributes are particularly useful for us to actually make structural interpretations. For example, end tracking, right? It's a very famous attribute, right? And end tracking is actually useful for us to actually pick faults. It's actually a technique for us to actually pick the faults automatically, right? So if we actually compute this end tracking attribute, it's going to try to delineate possible faults inside of our three-dimensional volume. Um, so all those attributes are kind of useful for us to actually do structural interpretation. Stratigraphic methods. Sweetness actually belongs to one of those stratigraphic methods, right? And then depth conversion, basic attribute, AVO, right? AVO attributes, amplitude versus offset, offset, amplitude versus offset, cross plot, priest accelerator, AVO attributes. So there are lots of attributes that we can extract from the seismic volume, from the original amplitude seismic volume. Right? But what's actually the purpose for all those seismic attributes, right? And how do we actually use those seismic attributes? One of the things for beginners, one of the things that you have to realize that multiple attributes could measure similar property, right? So there are duplications. One kind of property could be measured by using multiple seismic attributes, and in this kind of situation, you don't really have to sort of try each one of them, right? You just pick the one that actually works best for that particular property, and then just stick with that particular attribute, right? You don't want to duplicate attribute. You don't want to duplicate the same kind of calculation, right? So what you want to do is to discard those duplicate attributes, right? And a second thing is that seismic attributes should have a geological meaning, right? If you are not exactly sure what an attribute actually means, or if you are not exactly sure what's actually the geological, geophysical meaning of a particular attribute, suppose it's just purely just a mathematical transform, then it's not a good idea to actually use it at all. It doesn't mean just because it's listed in this particular table or in this particular list doesn't mean you have to use it. It's you want to pick an attribute that actually gives you specific geological, geophysical meaning for your particular project or for your particular reservoir, right? That's probably just the two most important principles for beginners to understand, right? First of all, there are duplicates. You don't want to sort of use duplicates, right? You just want to pick one that's kind of worked best for your particular volume. Second thing is that you want to pick an attribute that has specific geological, geophysical meaning or correlation with your specific structure, right? You don't want to just pick a random one that's just a purely mathematical transform, right? So let's try to extract some attributes. Let's try to pick one that's from maybe structure methods, right? Maybe basic attributes. Let's look into basic attributes, right? Say RMS amplitude, right? So it's always a good idea to actually just look at what's underneath the question mark. RMS amplitude computes RMS, root mean square on instantaneous trace samples over a specified window. Default is 9 samples, right? So if you actually look into parameter, the default of the window length is 9 samples. So on the vertical axis, it's gonna have a window length that's 9 samples, right? And then it's gonna compute the RMS amplitude for every trace, for every seismic trace. And on every seismic trace, it's gonna have a moving window with that's 9 sample wide, and then it's gonna move across all the time samples. Right? Let's just let's compute another one. Let's insert one more, and then this is amplitude information, right? Now let's try to extract some kind of phase information. Say instantaneous phase, right? Let's just try to extract these two kinds of and then for instantaneous phase, the default parameter, again, let's look into argument of the analytic signal, phase, right? So instantaneous phase is going to completely remove the amplitude information. So it's going to just get rid of all the amplitude information. It's more or less like a kind of automatic gain control, right? Except that it's equivalent to actually having the automatic gain control with the kind of ultimate choice of the parameters, because it's going to completely remove the amplitude information, basically, right? Let's just click on OK. Oh, not for the reason is that I didn't actually specify what's going to be the input and output, right? So for the first, let's specify what's going to be the input. So we're going to select the realized original seismic volume and then put it in there, right? And then the output is just going to be, let's give it some arbitrary name. Let's just call it RMS amp. Right? And then for the second one, let's still just use the same input, and then inst phase. Right. Let's just click on OK. So now we have two volumes. We have two volumes that's attached underneath the original amplitude volume, right? Suppose we turn off the realization of the display of this thing, and then just look at RMS, cross line, and inline, right? That's more like the amplitude information, right? That's just the purely amplitude information. Right? And at this point, the inspector becomes really useful. If we click on the inspector, right? So it's going to give us the inspector window, and then let's just change our cursor to the pick mode, and then click on the RMS amplitude volume, right? And then the inspector is going to show the information about the RMS amplitude. If we look into manipulate, style and resolution, intersection, attribute, parameter. The thing that's really useful is actually the attribute parameter, right? But because this time it actually allows us to actually adjust this window width dynamically, right? And you can see as we actually make the window width wider, the effect of the visualization actually is going to change in the graphic window, right? If we make the width wider, now it's like 32. You see this kind of a block. It's kind of the vertical block, those kind of thing, right? And then if you actually make it smaller, then it's going to become narrower. This is 13 points, 7 points, right? Become narrower. The features becomes narrower. Right? It's 4 points, 3 points. So once you have selected a good visualization, once your effect is kind of clear enough, the effect is clear enough, you can let me just let me give it like 5 or something. Right. Suppose you have found the optimal choice of this particular attribute parameter, then you can just go back to right click on the volume, and then there's going to be an option that's called realize, right? And at this point you can just click on realize. Yeah, let's just realize it. So after the calculation is completed, let's and now you have a RMS amp that's realized, right? At this point you can just turn off this thing and then display this one. And it's also going to give you a time slice, right? It's not just the inline cross line. You also have a z equals to something, right? That's sort of in the middle of the volume, right? And let's change our cursor to the small hand to the viewing mode, and then look at those seismic attributes. So usually amplitude information or amplitude attributes or those attributes that's kind of based upon amplitudes are kind of sensitive to lithology, right? Because it's kind of related to the strength of the reflection, right? How strong it actually reflects the seismic waves. So amplitude information are usually more or less sensitive to lithology, right? And again, because this is a realized volume, right? This is a realized volume. So one of the things that people may want to look at is so suppose let's right click on it and go to settings. And then opacity. No, let's first let's enable volume render, right? Let's just turn off interpolation and then go to opacity, right? So we looked at this opacity tab before when we were trying to sort of examine the raw seismic volume, right? But now we have a realized RMS amplitude volume. We can still apply the same kind of operation to filter it, right? Suppose we want to just right. So this is going to give us some kind of visualization about large RMS amplitudes, right, and where they are. Right. This kind of opacity plot allows us to actually visualize it. Oh, I actually forgot to click on apply when we did the interpolation volume render thing. But maybe this is not really a very good visualization. So let's still change it back, right? Doesn't really actually tell us too much of a useful information. and that's RMS amplitude, right? So, and then we also have instantaneous phase, right? So this kind of instantaneous phase is going to give us a better indication about the bedding of the system, of the reservoir, inside of the reservoir. So again, we can use the inspector. To examine the volume and make adjustments to the parameters. Or do I have a change the color scheme? Instantaneous phase sharp. Does not seem to be sort of particularly sensitive to this particular window width parameter. Right. As I actually drag this thing over, it doesn't seem to change the instantaneous phase by too much. Right. Again, once you have found the optimal parameter, you can just realize the volume and then do other counter visualizations of the same volume at different. So all those attributes are essentially there to actually help us to make interpretation. The most useful attributes for this particular data set has to be found by experimentation, right? Experience also plays a very important part. But let's still go back to the visualization of the original amplitude, right? And that's volume attributes. That's volume attributes. And sometimes we would like to actually look at the surface attributes, right? Those surface attributes are kind of attached to a particular surface. So again, we have lots of attributes that we can choose from. If you click on all, then we have amplitude attributes, right? And then we have statistical attributes, signal shape, measurable interval, that kind of thing. Right? Supposedly we're looking at amplitude attributes. We have average energy, average magnitude, that kind of thing, right? So suppose let's just choose average energy, right? And then we have to select the seismic data. Let's just pick our realized volume as our seismic data, and then add to surface, right? So where do we what's actually the surface that we want to add to, right? Suppose we have horizon interpretation, right? So suppose we pick a top tarbert, right? So these horizon interpretation are not exactly surface data; they are just the interpretation data, right? But this box should actually take interpretation data as well, right? It doesn't have to take a surface data. But if you want to sort of use surface data, you can just do a make surface first, right? Click on make surface and then create a surface using those interpretation data, and then use that surface to inside of this particular box, right? And then the window specification is going to be anchored around this particular surface. You can sort of see there are different choices. So single horizon, Z to Z, that kind of thing, right? And then horizon to horizon, right? So if you choose horizon to horizon, then it's going to compute the kind of attributes within a certain interval that goes from the top horizon to the bottom horizon. So you can specify what's actually going to be the reference horizon, right? Suppose the reference horizon is top starboard, right? And then the second horizon, and then let's say top knees, right? Or maybe it's not a good idea. Yeah, let's just use that, right? And then but let's add to the so let's just do the entire interval, right? So base Cretaceous as let's use base Cretaceous as the reference horizon, and then just use top eve as the second horizon. So we're going to compute some kind of attribute which is called the average energy for the entire volume that goes from base Cretaceous to top eve, and then the computed attributes are going to be attached to this base Cretaceous surface, right? So that's by using horizon to horizon. And then if you don't want to sort of stick with this particular top horizon, you can specify a certain interval that's from event above say largest peak, right? And then search window like 10 milliseconds, that kind of thing. So horizon offset, maybe let's just give it 0 or something. So those numbers actually come from how you actually did the interpretation. If you're tracking the peak or if you're tracking the trough, right? And then if you want to sort of make sure that your attribute is compute, those numbers are sensible, you might want to sort of look at the so if you actually click on one of those interpretations, you can if you right click on one of those interpretations, you're going to have something that's called operations that's going to allow you to actually shift the entire interpretation surface up and down by a certain amount, right? So operations, right? And then seismic operations, create interpretation. Oh, this is not. Maybe I clicked on the wrong thing. Survey one. We click on survey one. Operations. Right. So now you have, for example, arithmetic operations, right? So you can shift the entire integration up and down by a certain amount, and then try to actually come up with the correct number for the search window and horizon offset, right? And shift it a little bit, just see what's actually going to be the correct amount of the shift, right? And you can do the same thing for the second horizon, right? To event below, and then so the largest peak, right? And then specify a certain time window, say 20 milliseconds, that kind of thing, right? And all those numbers can be actually computed by using those by looking into the arithmetic operations thing, right? But let's but let's still change it back to 0. So for this demonstration purposes, let's not make it too complicated, right? And then resample parameter amplitude should not be resampled at 4 times x, right? You can adjust how it's going to be computed, what kind of data is going to be used for those. What kind of resampling can be used for those for computing those attributes. Yeah, now you can sort of see how this thing actually looks. This is attached to base Cretaceous, right? So it's attached to the base Cretaceous interpretation underneath the interpretation folder, right? And I was wondering if we can actually use the two-dimensional window. Let's go to the two-dimensional window, and then that's going to give us some kind of a visualization about the average energy, right? Let's see if I can automatically adjust the color. It's not really making any adjustment to the color yet. I probably should have realized probably should have just compute the surface first, and then use that surface as the so it did not actually allow me to change the color table by a huge amount. Right. So that's one of the ways for extracting surface attributes, right? Let's still go back to the 3D window. So it gives us some idea about the lateral heterogeneity of average energy, right? How it actually varies. How it actually varies. Right. Maybe let's try to compute another one. But this time let's try to compute something else. Maybe signal shape, right? Still just use amplitude. Try RMS amplitude, but this time maybe let's just use the surface data as some kind of control. We have surface data actually. Oh, but it's not in the. I think it's not in the time domain. It's actually in the depth domain. So we probably still have to do a make surface in order to actually come up with the surface data. So, but it's actually not difficult. All we have to do is to click on make surface. Let me just delete this one, and then let's just point it in there. This is a time domain interpretation data. So, oh, and then let's still just use the boundary from. Let's just use the project boundary. And automatic. Okay, so now we should be able to actually have a folder that's called horizon interp, right? BCU. This is a surface data now that's interpreted. That's interpolated from the interpretation data, right? And then top Eve. That's the two surface data. And now let's try to use these two surface data to extract some kind of surface property from such interpretation, such surface attributes. And now let's compute the, say, RMS amplitude. Mass amplitude, that's the add to surface. Yeah, that's just, do we want to try a different thing, say single horizon? And then if we are using single horizon, then we can specify the reference horizon, and then from event that's above the single horizon with a certain kind of interval, and then to an event that's kind of a certain time that's below the reference horizon, right? And then if we are using Z to Z, then we can specify the kind of a millisecond interval, say from minus 1850 to like minus 1950 milliseconds, that kind of thing, right? So, but let's still use horizon to horizon, and then let's just compute it and see what's going to happen, right? Oh, I forgot to. I forgot to change the horizon from the data to the surface. From the interpretation data to the surface, actually. This is actually still using the interpretation data. It's not using the surface. Just re-add it. Then top A. Oh, I see the polygon. That's the shape of the project boundary, but the project boundary actually extends beyond the seismic volume. So it's probably not a good idea to actually use that project boundary when we actually make the surface. Right. So we have those kind of extreme values along the boundary of the seismic data. So it takes some practice to actually understand how each of the seismic attributes to give us different kinds of information, right? But in general, we have certain classifications or categories about amplitudes, about seismic attributes, right? The ones that's kind of used quite often are those amplitude attributes. That's just give you some visualization or some kind of attributes that's related to the amplitude of the signal. And then we have phase attributes, right? Phase attributes. So the amplitude information is like detached from phase attributes. A phase attributes is just going to be some kind of a attributes that's just related to the phase of the seismic signal. And then we have frequency attributes, right? Frequency attributes. Those frequency attributes can be quite useful for indicating if it's oil or gas, right? Because those hydrocarbons usually give us some kind of dispersion, right? So and with attenuation, and those frequency attributes allows us to actually detect those kind of subtle variations in dispersion characteristics. And then we also have structural attributes. Those structural attributes allows us to better detect those faults and also horizons. Right? Structural attributes allows us to give us some help for structural interpretation. And some of the attributes allows us to actually visualize the relief of subsurface surfaces, subsurface horizons, that kind of thing. The relief, call it relief attributes, and then there's some other attributes that's kind of not exactly, cannot be sort of categorized into either of the, cannot be categorized into any of those specific categories, and those are just the so-called miscellaneous attributes. So some kind of random mathematical transformations that allows us to actually visualize the data in a different way, right? But again, we have to remember that lots of the attributes are actually duplicates of each other. Lots of attributes are highly correlated, right? So all we have to do is to just pick the one that's kind of works best for this particular project, and then sort of ignore those duplicates. Another thing is that not every attribute has a specific geological meaning, right? We want to pick the ones that's not just a random mathematical transform, but has a specific geological and geophysical correlations with the structure.